Is it okay? Okay. Well, we started functions yesterday. We talked about different type of functions. Mainly we had 4 type: one-to-one, many-one, onto, and into. Now one-to-one or many-one is in one option, onto or into in another option. So the 4 type again reclassified like this: maybe one-to-one and into, then many-one and into, one-to-one and onto, or one-to-one and into. So let us go for the 4 classifications: many-one into, many-one onto. Once it is onto, we call it surjection. So many-one onto is also known as surjection. One-to-one into means is again injection. So could be one-to-one into or one-to-one and onto. One-to-one and onto is surjection and injection. That means it is a bijection. So take care of these names. We'll be using it earlier and later. Now we go for a diagrammatic explanation for these functions. Can you classify these functions? 1, 2, 3, 4 is A, and B is 3, 4, 5, 6. 1, 3, 2, 4, 3, 5, 4, 5 is the function. But if you look into the diagram, it is very simple. It is obviously many to one because 3 and 4 have same image, many to one. And moreover, it is into because there are 2 elements having no pre-image. So it is into, many one and into. From that you have to see now. Hello.
Yes, sir. Can you explain into and onto again, sir?
Into, this is available. Into means there are 2 elements left out. If one element is left out in B, if one element is left out in B, then it is into. Onto means all the elements in B have a pre-image. That is yesterday's definition. You revise it. If all the elements in B have pre-image, then it is onto. This is not onto because there are 2 elements which have no pre-image. One-to-one means distinct elements have distinct image. Here x1 and x2 are different, but they have same image. So it is not one-to-one. So many to one. Okay, it is many one and into. Let's take next one. So this is many one into this one now. A is 1, 2, 3, 4. B is 3, 4, 5, 6, 7. A to B 1, 3, 2, 4, 3, 5, 4, 7. Let us see the diagram. Well, it is one to one. There is no 2 element with the same image. So it is not many to one. It is one to one. Again, it is not onto because there is no pre-image for 7. It is not onto. It is onto if all the elements in B have pre-image. So it is one-to-one and into, not onto. It's into. Are you getting what is onto, what is into? This is one-to-one. Previous one was many-to-one. Now let us take another one. A is 1, 2, 3, 4. B is 3, 4, 5. Now later you have to find out without diagram. Now diagram is very simple. It is many to one because 3 and 4 have same image. Now it is onto. Why? All the elements in B have pre-image. So it is onto. It is many to one and onto. Why many to one? 3 and 4 have same image. So many to one and onto. Onto means all the elements in B have a pre-image. This is onto. If one element is left out in B, that will be into. Now look at the 4th one. A is 1, 2, 3, 4. B is 3, 4, 5, 6. A function f is 1, 3, 2, 4, 3, 5, 4. What about this? This is one to one and it is onto. It is one to one and onto. Injection and surjection. It is a bijection. Once again, I'll make this clear. This is many one into because there is 10 has no pre-image. What about this? It is many one and onto. Clear? Many one and onto because every element in B has pre-image. What about this? It is 1 to 1 and into, because 10 has no pre-image. This is 1 to 1 into, and here 1 to 1 and on. Clear? All the definitions are clear. Many one into, it is many one because at least one pair has same image, so many one. There is no function like one to many. There is nothing like one to many. One element cannot have two images. It will not be a function. One element acts as two images. It cannot be a function. One element can have only one image, but many can have one image. That will be many to one. These two are many to one. These two are one to one. This is into. This is onto. This is also into. That is on. Well, now from this, let us have some properties. Let us discuss some properties, very important properties. Okay. Well, f from a to be a function where a and b are, be careful, finite sets. Number of a is less than b, then f cannot be onto. Can you imagine that? When number of a is less than number of b, it cannot be onto. Take an example from previous example. Here, a has two elements, b has three elements. Can you have an onto function? I cannot have onto function because one element cannot have more than one image. It will not be a function. So if number of a is less than number of b, it cannot be onto. What happens if number of a is bigger than number of b? Then it cannot be one to one. A has more element, b has less element, then it cannot be one to one. At least two elements must have same image. Number of a is more than number of b, it cannot be one to one. Remember it when a and b are finite sets. Now, range of f and codomain of f are equal. That is the meaning of onto function. In the codomain, all the elements are coming in the range. Range means, look at the range means it is only, suppose in this case, range is only 5, 6, whereas codomain is 5, 6, 10. Whereas here the range is 5, 6, codomain is also 5, 6. When the range equal to codomain, it is onto. When the range is equal to codomain, it is onto. Clear? The points are clear? Further, if a and b have equal number of elements, if it is one to one, it has to be onto, and if it is onto, it has to be one to one. Remember, I have precondition, a and b are finite sets. Okay, if number of a is m and number of b is n, how many functions are possible from a to b? I asked an earlier question, how many relations are possible from a to b? That was 2 raised to mn. Across b has mn subset, mn element, it has 2 raised to mn subset. Now the question is, how many functions are possible from a to b? Number of a is m, number of b is n. The number of functions possible from a to b. The answer is n raised to m. Let us see how that n raised to m comes. I'll make an explanation how you get n raised to m. Let us take example. A is 1, 2, 3, b is 5, 6, 7, 8. According to our formula, your m is 3 and n is 4. I must get 4 raised to 3. Let us see how I get. Let me take up the element 1. 1 can have only one image, maybe 5, maybe 6, maybe 7, maybe 8. But there are 4 possible images. Remember, 1 can have only one image. No matter whichever I select, there are possible images. Number of possible images. I am not saying number of images. Number of images for one is only 1, maybe any of these. But number of possible images for 1 is 4. No matter whatever is selected, number of possible image of 2 is again 4. No matter 1 has selected an image 5, 2 also can have the same image. 2 can have image 6, maybe 7, maybe 8. All the elements have now 4 possible images. By the fundamental principle of counting, 1 has 4 possible images. No matter whatever is selected, 2 has possible image, number of image 4. 3 also can have possible image 4. So total number of possible images will be 4 into 4 into 4, or 4 raised to 3. 4 raised to 3. 4 is n, that is n raised to m. Clear? Number of possible function from a to b is n raised to m, where number of a is m, number of b is n. You have to remember it because you have to encounter MCQs also. Now, under the same situation, A has m elements, B has n elements, number of one-to-one functions. Of course, when I talk about number of one-to-one functions, there must be one restriction that m cannot be bigger than n. M has to be equal or smaller than n. Number of one-to-one functions. Again, a question: how many one-to-one functions? The answer is npm. You know the permutation. Of course, m cannot exceed n. npm. Let us see how it comes. Again, how a and b. Number of a, that is m, that is 3. Number of b, that is n, that is 4. Well, if I take up any one-to-one function, I'm just picking a one-to-one function. One-to-one function need 3 elements from here: 1 to 5, 2 to 7, 3 to 8, or 1 to 6, 2 to 5, 3 to 7. Any. I need one set of 3 elements, not one set of 3 elements, one arrangement of 3 elements. I get one-to-one function. I don't say one set, one arrangement. It may be 5, 6, 7, 1, 2, 3, 5, 6, 7, one function. Maybe 5, 7, 6, another function. Another one-to-one function. Maybe 6, 5, 7. So any arrangement of 3 elements from this will be a one-to-one function. Every one-to-one function will take any arrangement of 3 elements. Any arrangement. It is not the selection. It is not the combination. It is the arrangement. Any arrangement of 3 elements from B out of 4 will be a one-to-one. How many are there? Out of 4, you arrange P, arrange 3. That is nothing but 4P3. Any arrangement of 3 elements from this 4 is a one-to-one function. Take another arrangement, maybe 6, 7, 5, or maybe 7, 6, 2, 3, 5, or maybe 6, 8, 5. Any arrangement will be a one-to-one function. So how many one-to-one functions? 4P3, precisely NPM. 4P3, that is NPM. Well, keep in mind this. As you are recording, you can upload it. Very careful. Something more, very important. Suppose a vertical line intersect the graph of y equal fx more than once. Remember, a vertical line intersect the graph of y equal fx. It cannot represent a function. Can you imagine why? Suppose I have a graph y equal fx. Now, any vertical line, if I draw a vertical line here, it will not intersect. Any vertical line intersect it more than once. What happens there? For one value of x, this is x, y1. For the same value of x, another y2, again a y3. That means for one value of x, for one x value, there are more than one y values. That is not possible. One x cannot have more than one image for a function. So it cannot be a function. Right? Further note 2. If any horizontal line intersect the graph of y equal fx more than once, then y equal fx is not one-to-one. If a vertical line intersect, it is not a function at all. If a horizontal line intersect, it cannot be one-to-one. It's simple. Then I have the graph, different graph. I draw a horizontal line. At least one horizontal line intersect the curve more than once. What happens there? There are distinct value of x1 and x2 at which the same y value. At x1 and x2, this is x1 value, this is ox, that is om, that is x1 value, on is again x2 value. At these two different values of x, y value same, correct? You have two distinct values of x. Pm if fx1, Pm if fx1, 2n is fx2, they are equal, but x1 and x2 are different. So x1 not equal to x2, but fx1 equal to fx2. So f is not 1. Well, 2 notes, be very careful. Well, some examples. This is revision. You are done in 11. Let us take identity function. What is an identity function? If it is from a to a, I call it IA. IA of x is x for all x. You know it. I don't need to spare much time. Domain is a, range is a. But if you have, it is a bijection. If you simply say IA, then domain is a. If you say IB, domain and range will be both B. But if you say domain and range of identity function I, set of real numbers. When I don't specify the domain, that means it is generally defined for all R. If I simply ask what is the domain of identity function, then it could be R itself. But if I specify I, then it is limited to A. Modulus function. You know what is modulus function? Mod fx, mod x. F from R to R fx equal to mod x, where mod x is, remember, x if x more than or equal to 0, minus fx minus x if x less than 0. It's called modulus. It is 11th standard topic, you know it well. Domain is R, range will be 0 to infinity, cannot be negative. Graph of modulus function, you know, is V-shaped, passing through origin. Okay. Constant function, fx equal to k, where k is a constant. It's a constant function. The domain is R, but the range is singleton set k. For now, every value of x, the function is only k. Well, signum. Signum means sign of number, plus 1, 0, or minus 1. If a number is a negative number, f of x is minus 1. If x is 0, f x is 0. If x is more than 0, f x is 1. F of 1.3 will be 1 because x is more than 0. F of 0 is 0. F of minus 3 is 1. Domain is R. Range will consist only 3 elements, minus 1, 0. I'm going past because these were 11th standard revision. The graph of signum function, that always you can refer. When it is equal to 0, it is 0. When it is more than 0, it is 1 itself. Less than 0, it is minus. Okay, greatest integer function, you know it. Fx equal to integer part of x. What is integer part of x? It is the greatest integer not exceeding x, not bigger than x. If we take, for example, f of 2.5 is the integer, greatest integer not bigger than 2.5, that is 2. F of 6.99, that is 6. If it is an integer, f of 7 is 7, f of 0 is 0. F of minus 4.2 will be integer part of minus 4.2. What will be that? Anyone? It is not minus 4, it is minus 5. Minus 4 will be exceeding this number. It will be not greater than this, it is minus 5. Integer part of minus 7.3 is minus 3. Be careful. Well, it is domain is R, range is Z, set of integers. The graph is also non-pure. It goes from 0 to 1, it is 0. 1 to 2, it is 1. At 2, again jumps to 2. It is actually a step function, or we also call it a staircase function. Okay. Further, polynomial function. F from R to R fx equal to px, where px is a polynomial in x, called a polynomial. Okay. What about the domain of every polynomial function is R? No doubt, every polynomial function has the domain R. What about the range? Be careful about that. If the degree of polynomial is odd, remember, then only the range is R. Otherwise, the range cannot be R. If the degree of polynomial is not an odd number, or if the degree of polynomial is an even number, the range cannot be R. What is the range? It depends on the given polynomial. But it is guaranteed if the degree of polynomial is odd, the range is R. Well, square root function, we know, f from R to R fx equal to root x, where root x is the positive square root of x. Fx is the positive square root of x. Well, domain is R dash. R dash means set of non-negative real numbers. Range is also R dash, you know it. Okay. For the rational functions, fx equal to px by qx, where px and qx are polynomial, where qx not equal to qx, rational. Right? Domain is R minus 0 sub qx, because qx cannot be 0. Qx equal to 0, it is not in the domain. This thing, second way, we studied it. Trigonometric functions, I'm not taking up details here. Further, you have inverse trigonometric functions, we will deal later. Exponential functions on the way. Trigonometric functions also I can explain in short later. Further, we have a logarithm. These are coming on the way, and I'm just telling what kind of real functions we are discussing now. Trigonometric functions, inverse trigonometric functions, exponential functions, and logarithmic functions. We are running short of time. Now down to 3 examples. Actually, I call it revisional questions. Find the domain and the range of the following functions. Be careful, you may have done in 11, but you may do it once again before we get along with the topic tomorrow. Well, Today I was speaking little fast because our time was little there was some constraint for our time. Okay, we'll meet back tomorrow with more and more exciting problems. All the best. We'll end by now.
Thank you, sir.
Bye. Bye.